Yes, Shivanka, is my screen visible?
Yes, actually, I want to ask something.
Yeah, yeah, please.
First thing that, sorry, actually, this time is actually not suitable for me. So can I have your like some contact, some mail? So like whenever you have time, you can answer me, like if it is possible.
Yeah, okay. Do you have any other friend who have joined this course?
No.
Okay. So because I was thinking to create a WhatsApp group, okay, so that if
Okay.
someone asks
Yeah.
some question, then I can answer those questions possibly. Okay. So that's why I'm asking. Okay, it's
Okay.
fine, and you can take my mobile number, and okay, you can ask any question in the WhatsApp. Okay.
Okay. Okay.
At which time you are comfortable?
Actually, just this 5 to 7. After this, at 7:30, I am free. 3 to 5, it's okay. Everything is fine. But just this time is busy.
Oh,
Not you only for this today, Saturday. Only.
okay. So, I mean, are you available on Sunday?
Yeah, yeah, yeah. Sure, it's very comfortable if we can arrange
Okay,
it.
then. Okay, then I will try to conduct this mentoring session on Sunday on the same time 5 to 7. It's fine?
Yeah, yeah. Sure. Please. Thank you.
Yeah,
Thank
okay,
you.
okay, I will do that. I mean, you can continue right now, Rol. Is it? Right now you will
Yeah.
continue it, right?
Yeah, yeah.
Yeah, okay.
Today actually up to 5:30 I'm there. So I had a question. If you can like, it's a very basic question, a starting question. So if you
Okay.
can, if I can ask, because I have few questions.
Yeah, yeah,
So
please.
like it is better like, yeah, if
Yeah.
you can open the very first lecture at 13 minutes 35 seconds.
Okay, wait. Okay, first lecture, right?
Yeah, very first lecture, 13 minutes 35 seconds near to.
Okay, lecture 1, 30 minutes. Okay, 30 minutes, 5 seconds. Here. Huh? Hello? Hello, are you here? Shivank?
Independent variable
Am I
x.
audible?
We
Yeah, yeah,
want
okay,
to
sorry.
minimize this.
Actually, I mute my call. Yeah, tell me where you have the question?
13 minutes 35 seconds.
13
13 1
minutes.
3
Okay,
13.
13 minutes.
Yeah,
13. Yeah, here. Yeah, tell me.
yeah. So till now what I understood, like this annex is random because it is arbitrary. So
Hmm.
generally we take some function, at
Okay.
least for one case we fixed it,
Yeah.
because it is arbitrary. So
Hmm.
like it can be anything, right?
Yes.
But once it is fixed, then the only variable is epsilon, right?
Yes. Then, I mean, what is your
Okay.
question?
Now,
I didn't get. Yeah.
yeah, my just next is my question is like, why we are like, how this Taylor series is applicable to functionals, because for function we can drive Taylor
Hmm.
series, but
Yeah.
how it is also because we see the curvature and everything, so we
Hmm.
can easily say that okay, Taylor series is valid. But how in such cases we can say that Taylor series is valid? And one thing, and the second thing is why we are taking it the about epsilon, like the variable is x, could be x,
Okay.
like why like, yeah. So there are two things. One thing, how come it happens, that Taylor series is valid for functionals, and the
Mm.
second one is like how epsilon we are taking that Taylor series about that epsilon because the variable can also be independent variable x.
Yeah, yeah. The question, the answers would be here. Taylor series not only bounded for a single variable. Okay, one thing it should be very clear that Taylor series not only bound for the single variable calculus. Okay, it is valid for the multi-variable also.
Okay.
Okay, this is one thing, and second thing is here I want to vary epsilon. Okay, I want to vary epsilon.
Yeah.
So that's why we have expanded it. Okay, because anyhow, I mean, if I take one example, like suppose I'm expanding, I'm just taking an example of sine theta. Okay, suppose sine x. Okay, wait. Yeah, okay. So suppose I'm taking an example of sine theta. Okay, sine theta, or you can say suppose it is x only. Okay, so you already know that whatever the expansion you got, it should be always a function of x, right? It should be always a function of
Yeah.
x. It's fine.
Yeah.
Now what I want to do is I want to write x as x plus delta x minus delta x. I want to write like this. Okay.
Okay.
So now if you want to expand it, you already know that this is nothing but sin x only. Now if you want to expand it, then it is nothing but it will be Maclaurin series where you are taking a naught as 0. That is nothing but the Maclaurin series where a naught is 0. So what we are doing is we are centering x at 0. We are centering it at 0.
Yeah.
Okay, so that's why it becomes
Yeah.
something like that f0 plus f dash 0 x plus f double dash 0 x square by 2. So which means that you can vary, I mean you can take any kind of variation here, any kind of function you can choose. Are you getting my point? So at that point, I mean that lecture,
Yeah, but
in that lecture, there we are taking x as epsilon. That's it.
but yeah, okay.
In that lecture, we are taking x
Okay,
as
like
epsilon.
yeah, but intuitively, I'm just trying to understand that if epsilon is definitely epsilon is very. I checked some other courses, like not courses, some other lectures and lectures and PDFs where I found that they have not applied Taylor series at this point of time.
Yeah, I
Like
mean they are
they took it in
maybe they would have taken I mean chain rule of the derivative, maybe chain rule of the derivative, or maybe they have expanded the derivative.
oh,
The thing is, this is the fundamental.
no, I checked. No,
Hmm.
just a minute. You have also explained the same thing actually.
Yeah.
In the I have checked your recording with the very first video.
Hmm.
There you say that the variation is delta y, right?
Okay.
That the variation from the from y delta is delta y, which is vertical distance between the. You have also explained the same thing. So they have done the same thing. They actually would find out that as we do in the differential calculus, that dy by dx, df by dx. Similarly, here we will say d del f y delta and variation of del. I mean to say that delta x here it will be delta y. You're getting my point.
Yeah. You want to say that instead of epsilon, it should be epsilon eta x. You want to say that, right?
Yeah, instead of epsilon, if in this expression, second last from the bottom, in this expression, if it is d epsilon instead of d epsilon, like here d I tilde upon d epsilon, instead of that, if it is written as b I tilde upon del y, means the variation, that is the variation, you have also explained the same thing, the variation, then the Taylor series can be understood. But if I just take the epsilon thing, then it doubts, it creates a doubt that how come I directly come to epsilon?
No,
Like
actually,
the what variation I'm looking at is,
yeah, actually, the
yeah,
Taylor
please go
series
ahead.
defined by this only. That is the thing. Taylor series is defined by this only. So that's why it can be written
Okay.
like this. If you take epsilon, I
Yeah,
mean
or
eta at boundaries like when y tilde becomes exactly like y, when boundaries are like this, I mean eta x1 equal to eta x2 equal to 0, then in that case Taylor series expand like this only. So that's why, I mean, this is the definition. It's not something
yeah,
like
like
you are
if
comparing
as you
from the,
explained,
yeah.
yeah.
Hmm.
No, no. As you explained it right now, like we can just put instead of x, we can put it epsilon. Look, mathematically, I don't have issue. Like we can put it in instead of x, we can get epsilon. Even here also, I can just get it. Look, epsilon is some variable. If we have fixed, uh, like arbitrarily, we have fixed eta x, then we have the only variable is epsilon. So we are taking it in the derivative. Intuitively, we can also think that it is a variable path which is defined by epsilon. So that's fine.
Okay,
But
okay,
if we take,
okay,
if we go by that,
let's derive this as per your definition, okay, and we will see what we are getting it. It's fine.
okay.
Let's derive by your way. Suppose y tilde equal to y plus epsilon tilde, right? And
Don't take epsilon, just take it delta y.
okay, let's take
Please take
that.
it, just erase it.
Okay, delta
Just
y.
take it delta y.
Yeah, okay. And y
That
is
delta, that kind,
what you are saying?
that kind of delta, that
Oh,
instead
okay, yeah,
that
it's
is infinitely small
okay,
delta.
yeah. That's okay. This delta, right?
Yeah, 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 yeah. Sure.
And y tilde dash, it should be y dash plus delta y dash. It's fine.
Yeah.
Now I want to write I tilde as x y tilde and y tilde dash dx, right? And I can also write y tilde as y plus delta y and y tilde dash as y dash plus delta y dash dx. Fine. Now I want to expand
Okay.
I tilde. So I tilde I can write as I. It's fine. I plus
Yes.
del I by del, what should I write here? Del I by
Del y.
del y
Del y.
and dy. Del y. Oh, sorry. Yeah. Dy plus del I by del y dash and del y dash. It's fine? Tell me. It should be, right?
No, I don't get it. Like, okay,
Wait,
I
wait.
understood your
Yeah,
point.
wait.
Let
Wait.
me see it because,
Yeah,
yeah,
here it should be I and del y equal to 0, and here also del y equal to 0, and suppose higher order terms. Okay, now it is the
okay.
same thing, no? It is the same thing. Here, here it should be I tilde, right? I can expand it like this, right? It's correct.
Yes.
Now
Yeah, you
here
can write it.
here it should be higher order term. Now when you write delta y equal to 0, then this term will become I only. Okay, plus, okay, here suppose I am also taking tilde also. I'm taking whatever you are saying it. Okay, so I am taking I tilde only. So when you take delta y equal to 0, when you differentiate it and when you take delta y equal to 0, then this will be nothing but del I by del y, this. I mean, what is the wrong here? Now you are saying that instead of delta y you are taking is epsilon
Like, just a minute. How you had written the second term in this first I tilde? I tilde. This is Taylor series expansion.
Yes, it is a Taylor series expansion for the multivariable. Here the variables are this and this. Here f is
Okay.
function of x, y and y dash. So this one is the zero derivative, this is the first derivative. Now when you expand further, the second derivative will come. Then at that time that will become del I tilde del y dash into del y dash. I mean the permutation will come into the picture, but that will be second order derivative. But this one is the first order derivative. This is the first order derivative.
Okay, I get
and we
it.
will not talk about the further derivative
yeah.
because we are already know that the delta will be very small. So that's why the multiplication, I mean when you go for the further derivative, then that will be very small. So that's why that will be 0. Okay, now you are saying that instead of delta y you are taking is epsilon eta. Okay, now your question is why you are taking epsilon
No,
eta.
epsilon eta. No. Epsilon eta is okay,
Okay.
but why we are taking this limit? This about epsilon is equal. Like epsilon is treated as x.
Yeah, this
Like,
is the definition of the Maclaurin series.
like we instead.
This is the definition of Maclaurin series. Taylor series.
If I just.
Yeah. Yeah, tell me.
If here I want to replace the delta plus del equal at every point by epsilon, like here I can write it at epsilon eta. Like instead of this first derivative, I can write it epsilon eta at del y is equals to 0. I can write it. I can say that the variations we can club. We can I find it at one place that it can be derived to such a point where eta x and epsilon we can say that one thing is epsilon eta and another thing variation is epsilon. To that point I can understand, but how we can change this del y is equals to 0 to epsilon is equals to 0?
Yeah, because only we are assuming that only epsilon is very small. We are assuming that only epsilon is very small. Okay, and we are taking delta as, I mean delta, instead of delta y we are taking as epsilon eta, and we already know that we don't know what is eta, it is arbitrary, but we are saying that epsilon is very small. Okay, that's why we can say that delta y is equivalent to epsilon eta, because we want to get the benefit out of that. So that's why we are writing here. So now we already know that since eta is very small,
Okay.
so instead of delta y I can write eta epsilon eta, and here also you can write, then eta will be cancelled out and only epsilon will survive. So that's why that will become del I by del epsilon and del epsilon. Are you getting my point?
Yeah, I get. And the most important thing which I'm missing is like I am treating it not as a second variable y and y delta. That's why y prime like this I am not treating as a. I think for functional there is some different proof. Like for Taylor series we have a proof like
No,
how
I mean,
the curvature.
for
matches.
any
I think that
multivariable
here
calculus, any multivariable calculus, suppose you have a multivariable function is something like f x y1 and y2. fx, y1 and y2. Then if you want to expand it, then you can write like z x, y1 and y2 as something like g x, y1, y2 plus, then you have to take the derivative of del f divided by del y1 dy1. I mean, in this case you can write del y1, okay, and plus del f by del y2 del y2. Like that you have to take the derivative. And here what you have to take? You have to take del, after taking the derivative, you have to take, suppose it is very small, then delta y1, suppose it should be tends to 0 and delta y2 tends to 0, and then higher order terms. This is the approximation of this function by Taylor series expansion, and this is because of the multivariable calculus. And when you take the higher order derivative, then it will become second order derivative.
Yeah, yeah, but here, like here, y and y1 are variable. But
yes.
Here, what we are doing here, it is function. So actually, my doubt is like how come it is valid for function also? Like if we are giving input as a function, then also Taylor series comes out to be valid. So that is the actually problem, because for variable we can easily prove, very easily we can give a proof of Taylor series that it is valid.
Yes.
But for function, how it comes that it also represents the curvature and everything.
Now it is clear, right?
Yeah, I will see into it, and actually I have very less time. So but I to some extent I get it. But my issue, like if you can get the derivation of how it is valid for functional also. Like if Taylor series for multiple variable is okay.
Okay.
But if the variable,
yeah, I will give you one. I will give you one
function
reference
itself.
book. I will give you one reference book. Maybe there you can understand. There is one book, Variational Calculus by Fomin. Okay. Follow this book. Maybe you will understand this.
Okay. And the just a 2-minute thing, like in the same slide, can you open that lecture? Just next slide in that lecture.
I mean, on the
Just
same
next
lecture
slide in
video,
14
right?
minutes. Next.
Yeah. Okay.
Yeah. Just next slide.
Yeah. Here.
Yeah, here. Yeah. So here, like what he said, that we are, by chain rule we are writing this.
Yes.
Because I tilde is depending upon x, y, and y tilde. So we are just writing it by this rule. That's fine. But the only problem is that again x is missing. Like we should also write, like we have written y tilde and y tilde prime. But x is also a variable. So we should also add one thing, that del f upon del x, then del y upon del epsilon. That should also be written.
No, actually.
Or x should not vary with epsilon.
No, actually, we are expanding this series by taking y and y dash as a variable. X will come automatically. Here, when you differentiate f with respect to y, then x will automatically come into the picture. You can expand Taylor series by taking any kind of variable. It's not something like here x is the variable. I mean, you can also expand. Suppose you want to expand.
No, what?
Yeah. Tell me.
No, not Taylor series. Not Taylor series. Just I am writing is if I tilde is equals to function of x, y, and y tilde, right?
Yes.
Y tilde and y tilde prime.
Yeah.
Right?
Yeah. I mean.
Now I just.
Yeah. Here the main reason is. Yeah. Here the main reason is the variation of y dash and y double dash is same. I mean, x is not varying for both functions. X is not varying. Did you see that plot?
Okay.
Here. Here, suppose it is y and it is y tilde. Okay. So the y and y tilde. For same x, these two functions are varying. For same x. So the main change in y and y tilde is not because of x, it is because of y only. If you take particular x,
Okay.
if you take particular x, then the difference between y tilde and y is not because of x, it is because of y. So that's why we are trying to find the optimum y. Are you getting my point?
Okay. Or I would say, yeah, or I would say like if because we are taking this differential of I tilde with respect to epsilon, and with epsilon x is not varying. With a particular epsilon, for a particular epsilon, x is not varying. That's why it comes out to be 0.
Yeah, in that sense also you can say. But intuitively you can see
Okay.
that the main change in y tilde and y is not because of x. So that's why we are not taking the derivative with respect to x, because we already know that it will be 0. Even if you take the derivative with respect
Okay.
it will be 0, because x is same for both.
Okay. 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 Thank you very much.
Yeah.
Yeah, thank you very much. Then, like, actually, I'm not. I will refer to what your books and something more,
Yeah,
and
please.
then I come back
Maybe
to
I'm
you.
not able to answer you correctly, but actually it takes time, and I mean, yeah, it will take time to understand. Maybe if you give some
Yeah,
time
I
and you
I,
try
I
to
may
understand
or
those equations, then you will get it. Okay.
yeah. Sorry, I today actually I'm free, but today and also I already I post you question before attend like so you can also like see it that to give me something to help me in a better way. Thank you for that, and thank you for providing the
What do
contact
you do,
number.
by the
Thank you
way?
very much.
I mean, are you BTech graduate or what?
uh, like I'm I'm master's graduate, like
Okay.
my postgraduate,
Okay. Okay. Okay.
and yeah, yeah,
Are you doing job, or I
yeah.
mean,
But
still
actually, I
doing?
am no, no. Actually, I just today I have to attend another session. That's why, like, I'm not able to attend. Otherwise, I will come. Okay.
No, no, it's fine. I mean, it's your choice. I'm just asking. I mean, what do you do
So,
after master? Are you doing PhD, or doing job kind of thing?
yeah. No, no. I'm looking for something. So that's
Okay, okay,
okay.
okay. It's
Yeah.
fine.
So yeah.
Yeah. Okay.
Okay. Thank you. Thank you very
Yeah.
much.
Bye, bye. Okay. So let's start uh, the session of this week. And in this week, we will try to solve some problem in two-dimensional case, and we will also solve the assignment problem for week 8. Not week 8, it is week 6. Okay. No, I mean week 7. So let's see. So this is the governing equation, which we already know that, where G is the heat generation, U is the temperature field, and it is a function of x and y. Okay. Now, either you will say that weighted residual, or I will write a variational statement. So the variational statement is like this. and if you plot, I mean, suppose there is an arbitrary body, and here this is the domain capital lambda n, and this is the domain lambda d, and here there is a heat transfer on this Neumann boundary, and suppose there is a heat generation G inside the body, okay, and here, so this is the case, and when you multiply with the variation and when you integrate with the whole domain, then we get this, okay, and here the whole lambda n, or here you can also say that this is del A is nothing but D union n, okay. So yeah, now I want to expand this term. So for that, what we will do is we will use the delta identity, that is delta u and delta dot delta u into w. So that is nothing but delta dot delta u times w plus delta u delta w, and this is the identity. This is the identity which we will use here. So it will become w delta dot delta u, that is nothing but this one, and this thing I can write like delta dot delta u into w minus oh yeah, here I am making mistake. It will be actually delta dot w delta u minus delta u delta w and dA equal to a gw dA, okay, and here we can see that it will become delta u dot delta w dA equal to, when you transfer here, it becomes gw dA plus a delta dot w delta u. Should be, this is not a delta actually, this is the nebula u d. Now what we will do is we will apply divergence rule. So here delta, I mean nebula dot w u dA, I can write w delta u dot n ds, or instead of that I will write d capital lambda, and then it will become del A, because we are doing now surface integral, okay. Earlier it was area integral, or you can say in two dimensional it is area integral, but in the same case, when you do the integral along this cross section area, it will be a surface integral, but it will be integral along this line. So that's why I am writing here. Now we already know that we can write q equal to minus lambda delta u. Okay, and when you take the dot product with n, q dot n, it becomes lambda delta u dot n, and here all these are actually vectors. Okay, and here in the problem it should be given, if it is given the Neumann boundary condition, then I can write q dot n equal to qn. Here it is qn because it is perpendicular to that. Okay, so suppose it is not qn, suppose it is q. Okay, and this is the normal vector, then when you project q on n vector, then it becomes qn. And if it is given that for a particular domain, if it is given that it is qn, then I can directly write in the place of del u dot n. Okay, so our variational statement becomes delta u, it is also a vector, dot dA equal to a zw dA plus, here it will be minus, so I should write minus lambda w qn d capital lambda. Now we already know that because of the Dirichlet boundary condition, from Dirichlet boundary condition I can write w at domain lambda d, it should be equal to 0, then this variational statement becomes now it will be integrated only on the Neumann boundary condition. Okay, so this is the variational statement. Okay, now what will I do is I will take a trial solution. I will take a trial solution UH as alpha I phi I. Okay, and what will be the derivative? So derivative will be alpha I phi I with respect to x, and what will be the derivative with respect to y? Okay, and for the place of w, we will use as phi I. So in that case, when you differentiate with respect to x, then it becomes ix, and when you differentiate with respect to y, then it becomes iy. Okay, so when you substitute all these things in the main equation, then we will get j equal to 1 to n alpha j phi jx phi ix plus phi jy phi jx dA equal to a g phi I dA minus phi I q n d lambda n. Okay, so here n is nothing but the number of nodes. N is what? Number of nodes. Okay, so what will be the kij then? This is when you expand the whole thing, then you can clearly write in form of matrix, and this will become alpha 1, alpha 2, alpha 3 and alpha n, and the right hand side will become f1, f2, f3 and fn. Okay, and here I will go from 1 to n, so that's why there will be n equation and n unknowns. Okay, so this is what? This is stiffness matrix. This is stiffness matrix. So if I want to write kij, then that will be nothing but the integral over a and n ix n jx plus n iy and n jy and dA. This is the stiffness matrix which we got. And now here we need to understand what is n, what is capital N. So now we will try to understand what is capital N, and we already saw that we need to write something like this: alpha I, phi I and summation. Okay, now suppose we are taking a two-dimensional element which is a triangle. Okay, and these are its nodal, these are its nodes 1, 2 and 3. Okay, then what will I write at the place of UHE? At the place of UHE, I can write UHE. I can write A naught plus not A naught, it should be U1 phi 1 E plus U2 phi 2. Okay, here I think everywhere I have written phi and later I have written n, so actually it should be phi, not, it should be phi. Yeah, so U1, U2 and U3. Okay, so we need to understand that UEH and suppose its coordinate is x1 y1 and this is x2 y2 and this is x3 y3, then UEH at x1 y1 should be equal to U1, should be equal to U1 and similarly UEH x1 y2 u2, it should be equal to u2 and UEH at x3 y3, it should be equal to u3. Okay, what does it mean? Which means that when we put the coordinate in this equation, then phi 1e at coordinate x1 y1 should be equal to 1, and phi 1e at x2 y2, it should be equal to 0, and phi 1e at x3 y3, it should be equal to 0. And similarly, if I write phi 2e x1 y1, it should be equal to 0, and phi 2e x2 y2, it should be equal to 1, and phi 2e x3 y3, it should be equal to 0. And this thing also I can write phi 3e x1 y1 equal to 0, phi 3e x2 y2 equal to 0, and phi 3e x3 y3 should be equal to 1. Now suppose I am assuming that phi 1e is something like this: a0 plus a1 x plus a2 y. Sorry, yeah, a1 x a1 a0 a1 x and a2 y. And similarly phi 2e, I am assuming that b0 plus b1 x plus b2 y, and phi 3e, I am assuming that c0 plus c1 x plus c2 y. And when we substitute all these conditions here, then we will get something like this: 1 x1 y1 1 x2 y2 1 x3 y3, and this matrix. a0 a1 a2 b0 b1 b2 c0 c1 and c2, and here it will be an identity matrix. Now we can see that we need this. Suppose it is a matrix A, so what it should be? A equal to, and suppose this is x and this is I, so this is nothing but x A equal to I. So what is A equal to nothing but x inverse identity matrix, and it is equal to x inverse. So if I want to get a matrix A, or if I want to get all those coefficients of these shape functions, then we need to take the inverse of this matrix. And here we need to understand this matrix is nothing but the area. If you want to get the area of this triangle, then if you take the determinant of this matrix, then it will be 2 times the area of this triangle. Okay, so yeah, so from this thing we can get A. Okay, now we can easily substitute in this equation, because we already know what is the phi, phi1, phi2, phi3 and everything, and then we can substitute and we will get Kij matrix. Okay, now let's move to our code and we will try to understand what it is happening. Let's take to understand all those, let's take one example, same class example, where we have a square plate where we have coordinate 0 0 1 0 1 1 and 0 comma 1, and here it is y-axis, here it is x-axis, and we are discretizing this element 1 and this element 2, and suppose this is node number, I mean this is the global, the white colored is the global node number, so 1 2 3 and 4, and suppose this green color is the local node number, so 1 2 3, okay, and 1 2 3. Okay, now we have to find what is the shape function, and then, and also there is a boundary condition here, and what is that boundary condition? Yeah, the boundary condition is Q n on the face, suppose I am writing here A, B, C and D. So it is saying that Qn on CD equal to 1, Qn on domain BC equal to 1, Qn on domain AB equal to 0 or adiabatic. And also it is saying that the temperature on the wall AD equal to 1. Okay, so this is the this is the Dirichlet boundary condition, and this is the Norman boundary condition. So this is the problem, and let's see how to solve it by using the code. Okay, so this is the shape function, and here we can see that first it will take all the nodal coordinate of each element, and then it will save in the variable x1 y1 x2 y2 x3 y3, and it will create a matrix, and this is nothing but the matrix X, and it will be stored in A by taking the inverse of this matrix. Okay, and then we will get all these phi1 phi2 phi3, and we already know that this is nothing but the coefficient, I mean the all the component of matrix A, because we can see that in this matrix we can see that this is the A11, this is the A21, and this is the A31, because it will be the transpose of A. If you want to get the coefficient of the phi, then it will be a transpose of A. So that's why it is not A12, it should be A21, and this is not A13, it should be A31, and then it will be save into the variable phi, and then it will return the shape function. Okay, and this is the force matrix. Let's see one by one, then we will take class problem. I have already done it, so that's why it will be easy to understand. So yeah, so here I have taken as a local, because we already know that for each triangular element the local coordinate will be always 1, 2, 3, and this is the global connectivity matrix. Okay, so which means that for the local coordinate, for the local node 1, what is the global nodal number for each element? So first row is for the element 1, so you can see that at the place of 1 I have to write here 1. Okay, and at the place of 2 I need to write 2 here, and at the place of 3 I need to write 3 here. And for element 2, at the place of 1 I need to write 3 here, at the place of 2 I need to write 4, and at the place of 3 I need to write 4 here. Now we need to write all the nodal coordinates, okay, in the global. Okay, so here we can see that the nodal coordinate for the first corner is 0, 0, and for the node 2 it is 1, 0, for 1, 1 and 0, 1, and then it will get all the number of nodes by taking the size function, the number of elements, then we will initialize the zero stiffness matrix. And here I will show that I want to get the stiffness, the shape function matrix as a function of x and y, so that's why I have initialized the symbolic variable x and y. And this integration limit is to get, because I want to integrate, so that's why I have written the integration limit for each element. So suppose for element 1, in this case I am taking element 1. So there are two ways to integrate on this element. Suppose you are taking a vertical strip, okay, which means that suppose the inner integral is y and the outer integral is x. So suppose the inner integral is y, then what should be the limit for y? It should be y equal to 0 to y equal to x. And what should be the x? So x should be 0 to x equal to 1. Or in this way you can also do it. If you integrate inner first then outer, then you have to take the strip something like this. Something like this. Then in this case we need to integrate what is the x, the lower limit for x is x equal to y, then x equal to 1, and then y equal to 0 to y equal to 1. Both way we can do the double integral, second order integration. So what did I do is, I have taken this. First I have integrated y, then I have integrated, both we can do it. Suppose I want to integrate x first. Okay, so what is the lower limit for x? The lower limit for x should be y, and what should be the outer limit, the upper limit? It should be sim 1. Okay, and what will be the lower limit for y? It should be 0 sim 0 and sim 1. Similarly, for element 2, this was the element number 1 and this is the element number 2. Okay, and in this case also I want to integrate in the direction of x. First, I mean the inner integration should be for x and then y. So suppose I want to integrate x first. Okay, then what should be the limit? So it should be x equal to 1 to x equal to y, because it is x equal to 1 and it is x equal to y, right? Yeah. And what should be the lower limit for y? So y equal to 0 to y equal to 1. So what I can write for x is 1 to x equal to y. And then sim 0 to sim 1. So this is the integration limit. Now this is the global node. Whatever you give, then it will be saved. I mean, it will be populated in the global nodes, and it will take local node. Then it will be integrate. It will the first for element 1. It will take the first row, k-local and stiffness matrix. Then let's see the stiffness matrix function. When you give the stiffness matrix, I mean the nodal coordinates and integration limit, then what it will do? You can see that we need to first differentiate all those shape function. Okay, we need to differentiate all those shape function. Let's differentiate all those shape function, then we will see what happening. Let's suppose I want to print yeah, printf okay. Then first it will give shape function for each matrix. Okay, so let's display this n, and we will see what it is giving. Okay, let's run this code. This is the nodal coordinate k global, okay, it should be sim 1, then it will be correct. Oh, I have taken 2. Sim y for element 1, sim 1 to x equal to y, sim 0 to sim 1. Yes. Yes, so now for element 1, you can see that what is the global node for element 1. The local nodes are 1 to 3, which we already saw that, and the global node is also 1 to 3, and for first element it will take the integration limit, and then it will print a shape function, and we will go into the stiffness matrix. Okay, and we already got what is the nodal coordinate for element 1. So 0 0 1 0 and 1 1. So initialized it, then it will display. So here you can see that it is the shape function for element 1, because when you write x equal to 0 0, when you write x equal to 0 0, okay, it should be something, because is there anything wrong here? Shape function matrix. Yeah, it's correct. So when you write x equal to 0 0, then you can see that it will be 1, and for other shape function it will be 0. And suppose and also for node 2, for this node, and this was the local node 1 2 and 3. For this node, when you put x equal to 1 and y equal to 0, so this will be 0, and this will be 1, and this will be 0. And similarly, when you put 1 1, then these two will become 0, and this will become 1. So this is the shape function for element 1. Let's go, and here yeah, stiffness matrix. So then first it will take the derivative of n, and then this is the derivative, and then it will be run for I equal to 1 and j equal to, sorry, I equal to 1 to 3 and j equal to 1 to 3, and this is the limit. And here we need to modify it, because first what we have written is the limit, the integration limit for x. So it should be the first, second, third and fourth. Okay, and also we are integrating x first, so it should be x minimum and x maximum, then we are integrating y, so y minimum and y maximum, and it is holding for both, so nothing to worry about that. So this is the stiffness matrix, and yeah, now okay, let's try to get the value of k local for element 1. Yeah, so here this is the k local for element 1. This is the same thing which we got in the class. Okay. Now to get the force matrix, let's see, we need to do some manipulation, and here I will also change the same thing. 1, 2, 3 and 4. Okay, and first we are integrating with respect to x minimum, x maximum, y minimum and y maximum. Okay, now we already know that, we can see from the natural boundary condition, then it is saying that on CD here Qn equal to 1. Let's talk about the first element 1. In element 1 it is saying QAB equal to 0. QAB, Qn equal to 0 here, and QBC equal to 1. Qn equal to 1 here. Okay. So what we will do here is we will split the shape function accordingly. Okay. So let's see for element 1. So if it is element 1, then what we need to do is I will enter e equal to 1, so that the if condition will be valid for that, and then it will integrate accordingly. Okay. Because here what are the boundary conditions? Normal boundary condition: Qn on CD equal to 1, Qn on BC equal to 1, and Qn on AB equal to 0. So yeah, so you can see that if it is element 1, then this part will run. Okay, and for this part we already saw that the force matrix for element 1, for E equal to 1, the force matrix will be something like this. And what it should be? It should be N1 W1, okay, and N2 W2, and minus, I mean it should be integral also, it should be an integral. Okay, integral, it should be N1 W1 N2 W2. Okay, now N1 G1, N1 G1, N1 G1, N1 G1, and DA minus what is there? It is the Neumann boundary condition, and what it is? It is phi I. Okay, so here I will write, at the place of n I will write phi I, phi 1 and phi 2, and here g will be constant because g is everywhere, it is same, and here it will be q times W1 phi 1, here it is phi 1, and q times phi 2 and d del n. Okay, now we can see that in this domain, when you integrate for this element, then this part is okay, and that is nothing but phi 1, and that is n. Okay, that is ni into g, and g it is already given that it is 1. Okay, so this part it is fine, but for the heat transfer on the surface, so that's why I have written minus int, and for the whole surface, here for the whole surface we need to integrate it. Okay, so we can see that for here there is no such heat transfer, so that's why there is no such contribution of this. But for here, for this domain, I mean for 2 to 3, we can see that x equal to 1. So what we will do is, for the same n, because here phi 1, so for the same n, what we will do is, at the place of x I will replace with 1. Now it becomes a function of y, this f sim, because f sim is a function of x and y both. So what we will do is, when you replace x with 1, then it will become a single variable or single order, I mean first order integral. Okay, and then we will integrate y equal to 0 to 1. Okay, and here there is no such heat transfer, so that's why there is no such contribution for that. Okay, and then we will store in it. Okay, now it will run 3 times, because for each n it will run. Okay, and similarly, suppose this is not an element 1, then what will happen? I mean for the element 2. So if we see the element 2, then what we will do is, this is the element 2, this is the element 2, this is the element 2. In this element here, we need to see what is the heat transfer on this surface. So what is the heat transfer on this surface? That is Qn equal to 1, and for this y equal to constant, and for that what we will do is, we will replace the variable y with 1, and then we will integrate x from 0 to 1. So that's why I have done it. Then it will store in init function. Okay, and what is that init function? It is zeros 3:1. Now I think everything is fine, stiffness matrix is fine, force matrix is fine, and yeah, so here you can see that if it is 1, then the first part of that f local will run. If it is not 1, then second part of the f local will run, then it will be stored in the init function. Now we will need to see what are the fixed nodes. Fixed nodes means those where we already know what are the temperature. Okay, and we already see that on the wall AD, that is 1 and 4 node are fixed. Okay, and free nodes are those more nodes where there is no such temperature, I mean there is no such Dirichlet boundary condition. So here the free nodes are 2 and 3. Okay, and then it will take k reduce and f reduce, from that it will print, okay, k reduce f reduce, and here what it will do, it will find u reduce and k reduce. Okay, but there is a catch here, f reduce is not exactly this, but it should be something else, because here it is not a temperature, it was not a 0 temperature, that's why we need to change the f reduce. Actually I already created that, let's see. Yeah, I'll copy this thing. Yeah, I have copied here because f reduce, what is the f reduce? F reduce is the f global from the free node minus, here we already know that this is the k global and this is the temperature and this is f. So this is the u1, u2, u3, u4, f1, f2, f3 and f4. Okay, and it is saying the temperature on wall AD, I mean 1 and 4, we already know that u1 equal to 1 and u4 equal to 1. So k11, k12, k13, I mean whatever it is, we don't know. Okay, so let's mark this. Okay, so we need to extract this k reduce. This is the k reduce. This is the k reduce. Okay, and this is the u reduced and this is not the f reduced. Okay, this is not the f reduced, but f reduced equal to f2 f3 minus these four thing, that is, what is that? k 21, k 24, k 31, k 34, and what is that boundary condition at that point? I mean u1 and u1, so it should be 1 1. Okay, this is the f reduce. Okay, so that's why I have written k global, free nodes and fixed nodes. So what are the free nodes and fixed nodes? Free nodes are, let's run this code, then we will get it. Force matrix, what happened in that? Yeah, here it is a mistake here. One, two, three, and 4. Okay, let's run this code. Okay, anyhow we are integrating x mean and y, because in both case what we are doing is we are doing inner integral with respect to x only, so that's why it is giving an error. Okay, what else are fine. Okay, let's solve. Hopefully it is correct now. Okay, so here we need to see that what are the fixed nodes. Fixed nodes are 1 4 and 2 3. So from the k global it will extract 1 2 1 3 2 4 and 3 4. Okay, whatever we saw it. Okay, this is 2 1 2 4 3 1 and 3 4. It will extract and it will multiply. It will multiply with fixed nodes where it is 1 1 and 1 2. Okay, so we need to give it. Okay, what is the fixed node here? Fixed node is 1 4, but we have not given the value 1 4, so we need to give value 1 4. So let's give let's initialize it. Okay, and here we need to write u1 equal to 1, u4 equal to also 1. Okay, these are fixed nodes, and after getting that if reduce, then free nodes equal to u reduced. Okay, now it should be fine. Yeah, let's see to run this code. So here it is reduced stiffness matrix, now reduced heat transfer matrix. Okay, and then you will get u reduced, then here, yeah, here we need to erase this, otherwise all the entries will become 0, because after getting free nodes we will get u reduce, and fixed nodes we already know that. Okay, so let's run this up to this point. Okay, so here we can see that it is saying that the temperature 1, 2, 3 and 4, and as expected here the temperature is 1, I mean T4 equal to 1, and T1 equal to 1, and T2 equal to 3.33, and T3 equal to 6.333. Okay, and these are the heat transfer on each nodal points, and let's interpolate it and we will see how the T looks like. Okay, so this is the plot, and this will be always a plane when we take a first order two variable linear function, so we will always get a plane. So here in this case you can see that this is x-axis, this is a y-axis, then the temperature on this whole wall is always 1, and the temperature is highest here, and at this node the temperature will be 3.33. so this is the temperature profile. Here you can see that the temperature is actually gradually increasing. Okay, so yeah, this was that part. Now let's see the assignment which we got. in this week. So again, the element 1, element 2, there are two elements, and for element 1 you can see that at local node 1 the global node is 1, for 2 2 3 3, and here for element 2 1 is 3, 2 is 4, and 3 is 1, and these are the global coordinates. For this it is 0 0 2 0 0 2, it should be 0 2, okay, 0 0 2 0 and 0 2. Okay, so here also, because we are considering 4 nodes, so that's why 0 0 2 0 and here 1 1. Okay, how it is 1 1? I mean, nothing to worry about that. We already know that all angles are 45 degree. So if all angles are 45 degree, then its length is 2 2, then this whole length will be 2 root 2, and if it is 2 root 2, then this will be root 2 and root 2. Okay, and if it is root 2, then it will be also a root 2. Then since it is angle is pi by 4, then it will be root 2 sine pi by 4, and this will be root 2 cos pi by 4. So that's why this coordinate is 1 1. So this is the node number, node element, everything is same. Now let's see the element. We are taking two elements, so element wise what are the boundary conditions? So for element 1, if we take the strip along x axis, then it will be x equal to y. So let's take this element 1. Element 1, this equation is x equal to y, and this is what? This whole line is nothing but x plus y equal to 2. So if I want to write in terms of y, then I can write x equal to 2 minus y. Okay, and this whole height will go from 0 to 1. If I take horizontal strip, then the lower limit of x will vary from x equal to y to 2 minus y, and y will vary from 0 to 1. And similarly, if you take element this element, it is something like this. Okay, and again here we need to take care that you cannot take horizontal strip, because if you take a horizontal strip, then you have to integrate twice. Okay, so that's why I am taking vertical strip. In this case I am taking vertical strip. Okay, and for that vertical strip you can see that this is y equal to x, and this is y equal to 2 minus x, and again x equal to 0 to x equal to 1. Okay, so for y limit, for x limit I need to write 0 to 1, and y limit x to 2 minus x. So these are fine. And again we can see that for these two elements we need to perform the integral. I mean, in the first element we need to perform inner integral first with respect to y and then x, and for this element we need to perform with respect to y for inner and then with respect to x for outer. So that's why the same shape function will not work. So for the same stiffness matrix will not work, so that's why we need to change accordingly. So here for element 1 you need to see that first we need to integrate with respect to x and then with respect to y, and similarly when it is element 2 then first it will integrate with respect to y, then it will integrate with respect to x. Okay, and is there any heat transfer? There is no such heat transfer, but yeah, there is a heat transfer on this wall, so we will see in the force part. So yeah, force matrix. So in this force matrix again we will do the same thing. We will first integrate for the first element, we will integrate with respect to x then y, and here we need to see that qn equal to 1, here qn equal to 1, but here qn equal to 0, and also here qn equal to 0, qn equal to 0. So we need to perform the integration in the force matrix on this region only, nothing to worry about this region. So for this region we can see that the whole y is 0. So the whole y is 0. So we will substitute y as 0, and since q equal to 1, then we will integrate from 0 to 2, because this region is varying from 0 to 2, and we don't have to integrate for this region because it is 0 already. And similarly for element 2 we don't need to integrate for this region because q is already 0. So that's why for element 1 only we need to integrate, okay, to get f, but for element 2 we don't need to perform the integration. But I have already written 0, but I mean nothing to worry about that. Even if you do not write, then it's fine. Okay, so yeah, it's fine. And also you can see that if qn is given on this region, then we need to see that at the place of x we need to write 2 minus y, and then y will vary from 1 to 2, but since q is already 0, so nothing to worry about that. So everything is fine here. Let's print shape function. Yeah, it is printing only shape function. And also we need to see the fixed nodes. Where are the fixed nodes? Fixed nodes are at point AC, that is 1 and 4. So 1 and 4 are fixed nodes, and yeah, u1 and u4 are 1, so that is also correct. Now let's run this code. Okay, so let's mark all these answers. So first it is saying the stiffness increase. We will see this result later. We will see, yeah, it is saying the stiffness increase Kij obtained from the weak form can be expressed at I mean it is the definition only. So what should be the answer? So you can clearly see that 1 Ix Jx, yeah, this should be the answer C. And now yeah, Ix, yeah, Ix Jx, Iy Jy, yes. Now it is saying force increase. So force increase, what it should be the force increase? So there is no such differentiation in n, so that's why ni dash is wrong answer. So this will not be the answer. Yeah, this will also be not be the answer. This will also be not. So correct answer is this. Now it is saying what is the element connectivity. So it is the same thing which we have already written. So we will see 1 2 3. So 1 2 3 and 3 4 1. So this is the correct answer. Now express the shape function n1. Let's see, we have already printed everything. So for element 1, what is the shape function? So you can see that this is the answer, 2 minus x minus y. And what is the shape function n2 for element 1, that is x minus y by 2, and express the shape function. This is y, so this is the correct answer. Now for element 2, it is asking what is the shape function for first, so it will be x only, so this is the correct answer. And second, it should be y minus x by 2, so y minus x by 2. The third will be 2 minus y minus x by 2, so this is the correct answer. And express the Dirichlet boundary condition for the above mesh. So it's clear that alpha 1 and alpha 4 must be equal to 1 because temperature on that wall is 1. Now it is asking what is the value of stiffness matrix for element 1, what is the K12. So it's clear that it should be 0, so 0 is the answer. K113, so minus 0.5, this is the answer. K221, so 0.5, this is the answer. K123, minus 0.5, this is the answer. K331, this is the answer. Now it is asking for element 2. For element 2, what is the K11? So it should be 1. What is K12 minus 0.5? This is the answer. What is K13 minus 0.5? This is the answer. Now it is asking the value of F2 of element 1 for heat transfer matrix. So F2 of element 1, it should be minus 0.666. So if you derive it, if you divide it, so 4 divided by 14, now minus 1 divided by 6. Okay. Okay, maybe we have made some mistake in the force matrix. Okay, it's fine. Actually, for element 2, for element 1, it is asking for node 2. Okay, that thing we need to take care of. Okay, so we need to see what we have assumed it. Okay, so from that figure, okay, that is fine. Node 2 only, that is node 2. Yeah, it should be correct. Is there anything mistake which I have done? I think everything is correct here. Let's see with the force matrix X. Okay, node 1 0 0 2 0 1 1 0 2, everything is correct. I think fixed nodes 1 4, temperature is 1 here, that is also correct. Okay, global fixed nodes. Okay, we will see later, maybe something is wrong with the answer. Now it is saying 4 element, same element, but third means 0.33, so it should be answer B. And for element 2, it is saying what is 2, so 1 by 3. Similarly, it is asking what is the value of alpha 3, that is the nodal temperature at node 3. So from our solution it is coming at 1, but since there is no such option for alpha 3, and similarly what is the value of alpha 2, that is also no answer. So we will see that because I have already wrote a mail to the professor, and hopefully I think it should be rectified very soon, but this is the answer which I got. Now let's see another problem where so the next problem, example 2, it is saying consider a steady state heat generation problem through a rectangular region as shown in figure. Material is isotropic with K equal to 1 unit. There is a heat generation G equal to 1 throughout the plate, okay, and the plate is something like this. Okay, and this width is 2 unit and this length is 1 unit. Okay, and we are assuming that A, B, C, D, and these are the global nodes 1 2, and suppose I am discretizing it, so I am assuming 1 2 3 4 5 and 6, and we are discretizing it such that we are taking 1 2 3 and 4 elements. Okay, and there are some boundary conditions. It is saying the side AB which means that heat transfer Qn on domain AB equal to 0. Okay, and it is also saying AB and AD are insulated. Not only AB but also AD is also insulated. Okay, and temperature on the whole domain AD equal to, given by a function 7 cos pi x by 2, which means that I can write T0, I mean AD, I can write T5 on, not AD, it is CD actually, it is CD. So I can write T5 is when x equal to 1, so it becomes 0, and T6 when x equal to 0, so it will become 1, so T6 equal to 7. Okay, and it is also saying the temperature on side BC is also 0. Okay, so BC means what I can write, T3 is also 0. So this is the problem which we have to solve. So let's see on the MATLAB code for this. So we are taking 4 elements. Yeah, we are taking 4 elements. Okay, so 1 2 3, so locally I will write here 1 2 3, 1 2 3, 1 2 3, and 1 2 3, 1 2 and 3. This red one is a local coordinate, okay, local node number. So for 1 2 3 you can see that it is 1 3 2, okay, and for 1 2 3 1 4 3, so for element 2 it is 1 4 3, and 3 4 5, so 3 4 5, and it is 4 6 and 5. Okay, and what are the nodal coordinates? 0 0 1 0 1 1 0 1 1 2 and 0 2. Okay, and yeah, this is the K global, everything is same. Now we need to see what are the boundary conditions. So for element 1 you can see that it should be x equal to y and x equal to 1, and y should be vary from 0 to 1. And for element 2 it should be x equal to 0 to x equal to y, and y should be vary from 0 to 1. And for element 3 it should be x equal to 1 minus y. Okay, this the equation of this line is 1 minus y to x equal to 1, and y should be vary from 1 to 2. And for element 4 it should be x equal to 0 to 1 minus y, and y should vary from 1 to 2. So these are boundary conditions for 4 elements. Okay, and these are the same thing, and there is nothing difference, and we will get F local, K local, and let's see what is the F local and K local. Okay, so here you can see that nothing to worry about that, because there is no such heat generation here. There is no such heat generation, so nothing to worry about that. Okay, in the problem I have written wrong, so actually there is no such heat generation, so Q equal to 0 here. If there is a heat generation, then we have to modify, we need to modify the force matrix accordingly. Okay, so there is no such heat generation, so this F will remain same for each element. And what is the shape function matrix? yeah, no, yeah, stiffness matrix. So this is the stiffness matrix. It will be also same, and let's see whether we are integrating correctly or not. So we need to first integrate x, okay, then y, and in the force matrix also we need to integrate x then y. Okay, let's run this code and we will see results. And yeah, we will also need to see the boundary condition. What are the fixed nodes? Fixed nodes are 2 3 5 6. Okay, so 2 3 5 and 6, these are fixed nodes because we already know the temperature at 2 3 and 5 6. Okay, so 2, where it is 2, yeah, 2 is also 0 because it is saying that wall BC is 0, so which means that T2, temperature at T2 is also 0. So 2 3 5 and 6 has 0 temperature. Okay, so that's why 2 3 5 6, yeah, and yeah, 6 is at 6. Okay, yeah, it is also given that T6 at 7, so that's why it is 7. And yeah, everything is correct. Let's run this code. Okay, so this is the solution. You can see that the nodal temperature, that is 1, is at minus 2856, 2 0 3 0 5 2 3 4 is here, and 5 is 0, and T6, okay, T6 at 7, so that's why it is 7, and these are the heat transfer. Okay, now let's see what is the plot which we are getting it. Okay, so this is the plot which we are getting it. So here you can see that T6 is at highest temperature. Okay, so this is the solution for this code. Now here we can see that every time we need to change the integration limit because of the shape of the triangle. Okay, here every time we need to change the integration limit because of the shape of the triangle. And suppose we have some arbitrary shape, okay, and if you discretize it, and that triangle is not something like a right angle triangle, and some triangle like something like we cannot able to find what is the equation of that line. Okay, suppose we have some arbitrary shape of the body. Okay, and if you discretize it, then every time to integrate over some arbitrary triangle, suppose this is the element, then it's not easy to get what is the equation of this line to integrate over this triangle. Then what we will do is we need to convert this physical domain. Suppose this is the element E. Okay, this is the element E, and these are the nodes. And then what we will do is we need to convert this physical space, this is physical space, to master space, then the same node will be converting into 1 cap, 2 cap and 3 cap, and this will become a right angle triangle for each triangle. And we need to do this by linear transformation, by using linear transformation. And by using this you will see that this x-axis will become zeta and this y will become eta. Okay, and integrating over this triangle will be very easy compared to this arbitrary triangle, because it is a right angle triangle, and the variation of zeta will be from 0 to 1, and eta will be also 0 to 1. And since it is a right angle triangle, then it will be very easy to get the shape function and every stiffness matrix, but that matrix will be in the master space. So in that case, you don't need to worry about the integration limit. Okay, so then it will be very easy to integrate. Okay, and we will see all this in the next mentoring session. Okay, so let's wind up this for today, and we will see next week.